Good morning. Welcome, everyone. Welcome to INSA. INSA stands for Institute of Mathematical Science, Institute of the Mathematical Sciences of the Americas, and it's a part of the University of Miami. It is doing a really great job to enhance, to develop an important mathematics center here in Miami with lots of connections with the United States and with the whole world, mostly with Latin America, because Miami is in a very strategic setting. They have these kind of workshops, many very interesting congresses, some prizes, several postdoc positions, and they are very happy to host this meeting. I hope we all will enjoy it very much. If you have any questions or so, I can try to help. Otherwise, you come to know Dania, who will be around, or also Natalia can solve all your problems. And welcome, Javier.
I would like I would like to say something about the program of this week. So, well, the first thing I want to say is thanks to IMSA because it has been a great opportunity to be able to organize this. And well, second thing is the idea Kelly and me had in mind is to try to bring together singularity theories and experts that are close to mirror symmetry, and we try to assemble a program in which two, well, kind of two communities are present. So when you give your lectures, beware that not everyone is going to be a specialist. So try to make them as easy to understand as possible because this is a mixed community. Okay, so I'll present the first speaker. He's Atsushi Takahashi from Osaka University.
Thank you very much for the introduction, and thank you very much for inviting me to this workshop. And I'm very happy to come back again to Miami. And I would like to thank for giving opportunity to give some introductory lecture on mirror symmetry and singularity. And so, actually, so today, so I couldn't imagine which kind of people coming. So I prepared from the very beginning, very elementary thing. So, okay, now I'd like to start from first mirror symmetry. It is not considered as a duality that exchanges the roles of algebra and geometry. And originally, it was discovered in the string theory as an equivalence between two n=2 superconformal theories from different origins, which implies isomorphism of state space. This will be a topological mirror symmetry part. And also isomorphism of rings of physical fields. This will be a part of the usual classical mirror symmetry on the isomorphism of Frobenius manifolds, and also it leads to answering and equality of patch functions. This implied by this equivalence. Since the discovery of the homological mirror symmetry by Korsvich, it's better to explain the meaning or the background of mirror symmetry in this way. So just the exchange of the roles of the algebraic object and the geometric object. And mirror symmetry is very important as it deepens traditional mathematics like singularity theory, while establishing unexpected connections among several mathematical fields that initially seemed completely unrelated. For example, the algebraic geometry and some representational theory of the non-commutative algebra and also simplex geometry and so on. But anyway, so I want to emphasize that from the very beginning, singularity theory plays an important role in the theory of mirror symmetry because weighted homogeneous polynomial with isolated critical points together with its symmetry group is expected to give an n equal to super conformorphism. So therefore, so it appears from the first. And so in particular, it's famous that they provide a large number of pairs xy of Calabi hypersurface with this property. Which exchanges in this way Hodge numbers on two different Calabi hypersurfaces. And this duality is the origin of the word mirror. So in the Hodge diamond, we can put a mirror to get a pair. Okay, but in the singularity, or especially, so it's very important, especially for singularity people, to understand mirror symmetry as a triple duality, not just the duality, but a triple duality among algebraic geometry, representation theory, and symplectic geometry. We know already several phenomena such as Mackay correspondence, Arnold-Strange duality, and so on, where we see mystery relationships among offshore curves or discrete groups, such as the rational polyhedral groups, and root systems, the algebras, and also the vanishing cycles and things. So we have some very mysterious but very interesting phenomena there. And so in order to make several ideas mathematical precise statement, we need to choose first some mathematical structure to be identified, and then consider or make the precise statement. So, for example, if we take a Frobenius structure, for example, there are three constructions known, and they are from Gromp-Hittin theory, and invariant theory of wide groups, and deformation theory via primitive form. And whose conjectural isomorphisms are known as the classical mirror symmetry. And if we restrict to the isomorphism vector spaces, then we get a topological mirror symmetry. So this is a sub conjecture of this the mirror symmetry conjecture. And on the other hand, if we consider derived categories or triangulated categories, there are also three constructions. So one is from coordinate shapes on algebraic variety, and another one is representation theory of non-commutative algebra, and also some Lagrangian Frege theory, and whose conjectural equivalences are homological means. So in this talk, in part one, I will explain the mirror symmetry of invertible polynomials, very particular class of nice polynomials, weighted homogeneous polynomials, and also mainly from the viewpoint of algebra. And in part two, I think Jorgen will give a lecture from the other side, from the geometrical perspective. Anyway, so I want to emphasize here, I'm sorry about to singularity people, but it's very important to regard holomorphic function of complex manifold with finite number of isolated critical points as a non-commutative smooth manifold, not singular. That's the important point. So I want to say that it's important to consider function itself, not the zero. That it is one of the points. And so why we can consider it as a compact. I forget to put compactness. Smooth compact manifold. I explained in the the theory of topological mirror symmetry of the invertible polynomial. Then, so if we consider in this way, then the category of matrix factorizations can be considered as the homotopy category of bounded complexes of vector bundles over this non-commutative. And this is the direct analog to derived category of shapes on smooth algebraic graph. But this is just today I want to say some philosophy, not the not. I'm not going to discuss the detail about this. Okay. So now I prepare from the first. This is the main object to consider today, invertible polynomial. So here's the definition, and it's a weighted homogeneous polynomial with a very special property, but I mean, it is controlled by this n by n invertible matrix. So we want to consider some matrix, but the initial data is just this n by n matrix, because entries are rational numbers. And so, here I put CI some coefficients, but by how to say renormalizing the variables, the i's, then we may assume that these are all one. And also by choosing suitable ordering of monomials, we can assume that the determinant will be positive. Usually we assume these conditions. But anyway, so very simple point. So the point is here. So F consists of n monomials with in n volume. Then the one feature is this. So in this case, the weights of variables are uniquely determined by this condition. So in general, for example, if we consider such a polynomial, maybe xl plus 1 plus yz, for example, this is a typical differential equation of the L singularity. But in this, if we take this polynomial, then the weight is not how to say unique. So in this, so this is a typical property of the invertible polynomial. And in this, so by this, by this was normalized. So I assume that the degree of f or weight of f is 1. Then, so here, famous classification result. Then any invertible polynomial f can be written as a Tom-Sebastian sum of these two kinds of polynomials, invertible polynomials, and they are called chain types and loop types. And so tomorrow, as I'm discussing about the category matrix factorization for this polynomial. But anyway, so instead of explaining the notion of the Tom-Sebastian sum, I'll explain in these examples. So, and so in the trivial case of first case, this is sometimes called the Feldman type, but so I include this into the chain type invertible polynomial. And this is typical example of the Tom-Sebastian sum of two polynomials. And this is the chain type polynomial, and this is the root type polynomial. And again, so therefore, there are totally 5 classes of the invertible polynomials in 3 variables. And also, this classification is very famous in singularity theory. So you can find this classification in the famous Arnold Kuzinza Polynomial textbook. So this is here in the singularity theory already. Then we are now going to discuss about the symmetry of the polynomial. And I'm only consider this diagonal symmetry, and also consider the largest one among them. So this is the group which respect the f, which acts diagonally on variables and respect it. And this is characterized by using an increase of the invertible polynomial, invertible matrix. So therefore, so this symmetry is also controlled by the combinatorial initial data, E. And so in mathematics, Landau-Ginzburg obviously is just a pair of a invertible polynomial with and a subgroup of the maximal symmetry. And so because invertible polynomial is weighted homogeneous, so they always contain this as a subgroup. So these two weights of variables. So this taking this subgroup of the symmetry corresponding to the usual Z grading. And also there is another important subgroup of the this symmetry group, G. This is the intersection with the SL. So we often interested in the Calabi-Yau hypersurface and so on. So in order to have that, we need to keep a holomorphic non-fair vanishing N form. So therefore, in order to keep this, we need this condition. So therefore, if we are discussing about the Calabi-Yau hypersurface, for example, in the weighted homogeneous, weighted projective space, then we, in that case, we need to choose a subgroup of the symmetry containing this Z0 and inside of the SL. Okay, maybe just one. I made a mistake here. I'm sorry. This is not Z but C. Okay, again C. I'm sorry. Okay, anyway, so now we're able to talk about the mirror symmetry. In order to do that, we need to introduce two notions. So in order to how to say the dual of the pair. So first we consider the dual of this polynomial. It is given by taking the transposition of the matrix E. Then again we get some polynomial, and this F tilde is called as the Berger-Hooge transposed polynomial of F. And this is the first part. And but before going to further, first Berger-Hooge consider this transposition because they expect the mirror symmetry. This mirror symmetry holds in physics. So the pair of F with the maximal symmetry should be equivalent to the another CST with the transposed one with the trivial group. And later, Bergman-Henningson generalized this as this correspondence. And here G is now a general subgroup of GF. And they consider the dual object to this one, G tilde. So in this way, essentially the Pontryagin dual of G. Anyway, so we can define G tilde in this way. So and consider the so they expected these pairs mirror dual to each other. So so it's very important to consider the how to say this duality property. And so the largest one will be the smallest one, and the smallest one will be the largest one. So and so in this way, so and the how to say the dual of dual will be the original one. So this is the duality property. And in some sense, there is a Galois correspondence. But so here I wrote, but so if G contains G0 as a subgroup, if and only if this dual of G is inside of SL, and again this is C. So therefore, or it's this, by this duality property, we can have a large number of pairs of Calabi-Yau hypersurfaces. So in order to discuss Calabi-Yau hypersurfaces, we need both conditions, and these conditions are behave very well under taking the dual also. Okay, now I'd like to explain topological measurement. So for invertible polynomial, we can so because the anyway, so starting from this polynomial f, we can consider these two objects. This is the first one is the very famous one, the Jacobian algebra. It is a polynomial ring divided by Jacobian ideals. And also we consider this omega f. So I don't know the good name for this. But anyway, essentially these are the same object, but there is a subtle difference. And actually, omega f is just a Jacobian module of free of rank 1. So in other words, if we choose a no-fair vanishing f1, standard n1 is okay, then we get an isomorphism as vector space. But here's the important, very important point. This is the nothing but the Calabi-Yau property. And through this isomorphism, it's possible to say that Jacobian algebra is a commutative Frobenius algebra. So this Frobenius algebra structure is not canonical one, but by choosing this isomorphism, then this gets such a structure. That's the important point. And so in general, or maybe later I'll mention, but this is the analog of the homology of polyvector field, and this omega f is the analog of the Hodgkin homology. So therefore, this isomorphism is nothing but the Calabi-Yau function or Calabi-Yau. And also, we are going to consider the some pair of f and symmetry group G. So we need to consider such a thing. This is again the very the user thing in, for example, in the Mackay correspondence. So consider fixed locus and restriction to the fixed locus. But here there is one important point. The restriction of the invertible polynomials again defines an invertible polynomial. So here a kind of the recursion process. And also, again, this is famous object in Mackay theory, the notion of age. It is a rational number given by this definition. Anyway, these are standard. Then now we can associate to a pair of f and the maximal symmetry group a vector space, or more precisely a cubic graded complex vector space in this way by using the age and the restriction of f, and so by this I mean the taking GF invariant form surface. And in the special case, so if a fixed locus is just origin, then we define this omega f g one-dimensional vector space spanned by this constant function on the point. So this is the typical example of such a case. So I want to explain this one by the simplest example. So in this case, obviously the maximal symmetry group is generated by this one, and also the transposition is the original one. And so therefore we get these vector spaces. So this is the original, the usual one, and this is defined by these conditions. And here, the important point is that here we see the one-to-one correspondence between this differential form and the constant function on the fixed locus. So this is essentially, this is the essence of the topological mirror symmetry. So the correspondence between the differential form and the function, or in general, the differential form over the fixed locus. And so again, I should say this. This vector space should be considered as the analog homological. And so we can say now the topological mean symmetry isomorphism between this particular pair. So it is just vector space, graded vector space isomorphism between these two. And in general, if by replacing this group by some subgroup of G, then we can state more. But after this, there are many works on this topological mirror symmetry, but they are complicated and difficult to see the essence of the proof. Okay, and so finally, for any G, any subgroup, this is the point. And in terms of the functions on for the Q bigraded complex super vector space, again this is the point. Omega f G and omega f tilde G tilde, we have the very simple and very readable proof within 2 or 3 pages of topological mirror. So it is stated in this way. And the E function is, so I'm sorry, it is a little bit complicated. So the definition, so for any, so if you take any subgroup, then this E function is a little bit complicated, difficult, but anyway, the statement is very simple. And in the special case, this E function is nothing but the usual one in some sense. So here, with certain generalization, in the usual case, PQ are in both integers, but in general, in these cases, they are both rational numbers. So therefore, here we have to put minus, for example. But anyway, so very roughly speaking, this E function is the usual one, and we get this duality property. This is the statement of the topological mirror symmetry for the Landau-Ginzburg options. So in terms of Hodge numbers, by using these coefficients, then this is equivalent to this duality property as expected. And also, so this is one symmetry of E function, but there are all, of course, the natural duality property given by the cell duality. So if our function satisfies this cell duality, so maybe so I'll explain a little bit later by simplest example. But anyway, so we have this one. So because these are, I didn't say, but by assuming the F, so we assume that the F and F tilde are invertible polynomials. That means they have only at most isolated critical points, so they are finite dimensional vector space. So together with this property, we can see that the pair should correspond to some smooth compact space. So, but because of this rationality of these exponents, then we should we need to consider how to say orbifold at least orbifold, and in general not space. And also we can define a dimension of the pair. And in this case, also it's important that dimension and this n are different notions. So in the classical, in the usual manifold case, they are the same. But in this singularity case, they are different. So and the dimension is defined in this way. And so I didn't say, but anyway, the weights are all positive. So this is not, this cannot be n. So they are different. And the dimension doesn't depend on any choice of G. The dimension is defined purely in terms of or the n by n matrix.
Why this number receives the name dimension?
Good question, but it behaves how to say from maybe first I will give you an example. So this is an example. So here, in this simplest case, this is the function. This is the final answer, and this comes from the weight of the differential form. And this, so therefore, this corresponds to the how to say the usual the generating function of the Jacobian algebra, and the time. So it should start from 1, and the last term should correspond to the dimension if we consider the how to say analog of the usual manifold theory. So therefore, in this case, we will get as a dimension 1 minus 2 over a1. So this is the dimension. And also later I'll explain in the categorical, or explain the categorical meaning of the dimension. And so, what to say? So here, therefore, so we get this is the, in some sense, general, generating function of the exponent in the classical sense. So therefore, we need to carefully distinguish the weight and the dimension and so on, exponent and so on. But so in physical terminology, the dimension corresponds to the conformal dimension. It's weighted to the central charge of the vertex algebra. Anyway, so here, if we consider this part, this is an or e function for this dual or f with the trivial group. It's nothing but the generating function of the exponents, and it's first given by simply. Okay, then I give a summary of this property of a set of exponents. So for simplicity, we assume that G contains subgroup G's. Then due to the said duality, the mean of the set of exponents is the n over 2. This is the meaning of this equality. And together with Volkan everything, we show this equation. It's the it calculates the so this one is essentially the variance of the spectrum, the variance of exponent, and it is given by this. And record it for a smooth compact scalar manifold of dimension d. Livko, Earth, and Borisov show that this equality on the variance of the Q for the compact force. And so we can see the difference. So here, this part, the second term is missing in this. This shows that the space for F, the pair F and G has a numerically trivial function. So therefore, also here, this is Milnor. So this is a natural generalization of the Milnor number. So Milnor number is the natural generalization of the Euler characteristic, Euler number of the manifold, and this D is the generalization of the usual dimension. There is a subtle difference. So here we don't have n, but D. This is, by this analog again, we can see this is the natural analog of this dimension. And so in order to have zero here, the simplest way is to set C1 to Z. Of course, because we consider a weighted homogeneous polynomial, then the plus of F vanishes in the Jacobian algebra. So that's another reason why we should have a numerically trivial function. And so in this way, starting from F and G, we should have something non-commutative, smooth compact space. And it is described in terms of the category matrix factorization. Okay, so first, before going to the matrix factorization theory, first I want to briefly explain some geometric sign. It was I think familiar to the singularity people. So again, we consider so first we started polynomial. So but here it consider it as a holonomic function, a holonomic number, and they consider the classical theory, but we need to upgrade to the categorical world. So first, the objects are essentially the same as the classical one. So we consider distinguished basis vanishing cycle in the middle of fiber of this F field. And so, yeah, I omit the details, but anyway, it is upgraded to some infinity category called the directed Fourier category. And so objects are, how to say, the vanishing cycles in distinct spaces. But so we omit the detail of this part, morphism part and multiplication part. Anyway, they are defined by Lagrange frame theory. And here
the middle fiber is like a germ, but you didn't.
So in this case, the point is that the F tilde is weighted homogeneous, so we can consider
At the origin.
at one. And so I gave a summary here, the nice property of this category, finite and Schmidt, and it has a free expression. This is the categorical notion of the distinct space. Okay. And so for the safety, yeah. Yeah, so these are very standard. These two are very standard nice properties. And the point is this. But anyway, this follows from the existence of this. And this is nothing but the yes, categorical characterization of the distinct space. So we usually consider. So this is in some sense related to the how to say categorical version of the Zafir anomaly. And so the last one, this one, means that corresponds to the fact that the distinct basis spans the middle homology. this is just a categorification of that result.
Can you tell us what is T?
T. Sorry.
In this
T was the derived prime category.
yes, but is there a geometric interpretation because the objects are vanishing cycles? What is
Yes.
T of one?
This is I wanted to skip that part, but anyway, the twisted complex of the distinct basis functions. So we can formally form a complex by using these objects.
You have a T to the I there, the calligraphic T.
Sorry, Ti.
Yeah.
Ti. Sorry, this is the translation function of the triangulated category corresponding to the orientation. So orientation is usually plus minus 1, but upgraded to Z. So
That is the question. That is the one.
yeah. So if we have our some cycle, then we need to we have orientation that corresponds to plus minus 1 in 0. So this is the orientation. We can upgrade it. We can upgrade this one to Z. So what to say? Very roughly speaking, we can by counting how many times what to say the Lagrangian rotate, then we can count such a number to get the translation function in derived fact. This is a very rough idea. So usually, if first we have this orientation, then if we rotate in this way, then we get minus sign in the homological. And again, we rotate in this way, we get 0 for the original orientation. But in the triangulated category, we found if we rotate in this way, then we get 2, not 0. We can count in such a way, and we can consider not only just the cycle, but
Objects are Lagrangians or Lagrangian?
Lagrangian together with
Who
graded.
is the locals?
More precisely, graded
Graded
right. But I wanted to skip that part. Anyway, so it's just a very rough sketch of the story. Yes, of course. Yeah, so if we consider this category or this one, we need to consider Lagrangian submanifold or vanishing Lagrangian vanishing cycle together with grading and also some choices coming from geometry. Anyway, I wanted to skip that part. I just wanted to concentrate on algebraic side. And please ask joking. But forgetting about the categorical level, so we can consider algebraically invariant on the homological group level or Grothendieck group level. It's root system. And in general, so this kind of generalization is given by Saito and called generalized root system. It's not just a root lattice and so on, but we need also a Coxeter element. So I'll explain these first. These stuff. So N is the middle homology group of the middle fiber, and I want to skip the definition or explanation. But anyway, this I is essentially the intersection form, but symmetrized one, and more precisely also the symmetrization of the Zeit-Feld form. Maybe again we need sign change or anyway. Usually, so I assume that this is the self-intersection of the vanishing cycle is 2 without any sign. And this delta is a set of roots in the usual sense, but defined by through distinguished basis in this way. And this is the monodromy group, and or in algebraic terminology, this is a wide group of the root system, and generated by these reflections. So this is the how to say Pythagorean monodromy or reflection on the homology level. And the last one, this is a bit not obvious. This is the Milnor model, and it is written as the product of reflections with respect to a fixed distinct space.
Atsushi. So I was expecting that N is a Grothendieck group,
Yes, exactly.
but it's not the primary definition.
Yeah, because I wrote but anyways for simplicity. Yeah, because so we can write down these how to say definitions just in terms of the classical terminology. So I want to how to say explain the categorical terminology. So this is the this N can be identified with the Grothendieck group of the derived category. But anyway, this is the usual one. And so if we start from the AD singularity or polynomial defining AD singularities, then this triple defines a finite root system of the corresponding type, and this C will be the Cox element in the while group. I'll explain the simplest case. So, are you doing? And in this case, so this defines a singularity of type A1 minus 1. And because the Milnor fiber is z-dimensional, so instead we need to consider the reduced homology. And it is generated by these alpha i's. This means the bracket means the class of point. And this, in this case, this I is nothing but the usual intersection form on the reduced homology. And the set of roots is defined in this way if we know the answer. And actually, so it's homology class defined by the difference of two distinct points on the fiber. And in this case, it's easy to calculate that the Milnor monodromy acts in this way. Alpha 1 goes to alpha 2 and so on. And the last one come back to A1, the first one. And what in this case, while group is isomorphic to the symmetry group, it's very easy to calculate. And under this identification, the Coxeter element is corresponds to the cyclic permutation of this type. So it's easy from this. And this is the typical result. And later, this kind of data we can find in the grading of the matrix factorization. And I'll explain it again. Okay, now I'd like to explain the algebraic side of the homological mechanism. So first, we need to consider some rings and gradings and so on. And so we consider the how to say? Sorry, I forgot. Yes. Instead of this finite group GF, we need to consider. It's interesting to consider the grading LF is a grade. Free abelian group divided by this kind of submodule generated by this element. And in this case, LF will be an abelian group of rank 1. And in general, it's not free. And the usual grading, Z grading, is can be found in this way. So by how to say, so there is a surjective map from LF, this orbital group, to the usual grading by sending these letters to twice of the weights of the variables and twice of the degree of the polynomial. So there is a subtle difference. So therefore, so I put here homological degree. Yeah. So usually the degree is counted by half of this, but it's how to say very convenient to consider this kind of homological degree in the categorical system. But anyway, and also by considering the suitable quotient of this largest one, we get some other gradings corresponding to the subgroup. Anyway, by using this kind of the grading, then we will finally get a Z-graded category, not a Z over to Z-graded triangulated category. And this is homological. So we consider the original polynomial ring as an MF graded algebra and so on in the usual way. Now we can consider graded matrix factorization. So if you want to consider the ungraded version, just you can forget about the grading structure. But anyway, so it's defined in this way. Essentially, the square root of the original polynomial f in terms of the matrix, it is nothing but the graded matrix factorization. And because so this is not a complex, so because this is obstructed by f. But if we consider this pair of polynomial ring together with central element f, then we can say about anyway this pair is has a structure of the so-called curved algebra. And in that terminology, this matrix factorization is nothing but a twisted complex. So again, we can continue the same story as the infinity, how to say, homological algebra, infinity algebra, or infinity category. So we can consider dynamic category and so on. So I first give example. This is trivial, in some sense trivial or quite easy, but it's very important. So we can consider this kind of factorization, and we can consider the short exact sequence in the category of module. And then by this, starting from this short exact sequence, we can systematically obtain this kind of matrix factorization. And the point is that, so in this, how to say, data or matrix factorization, what is important, we can find an easy algebraic invariant by forgetting.
I got lost in the previous slide.
Yeah.
So you have a matrix factorization is same as maximal Polynomial models.
Yes.
But the triangulated category structure you consider is different. So
Yeah, that's same. As a result, same.
Same.
Same. Yes.
So you
It
do
is
matrix factorization as maximal Polynomial models, and then you have the derived category of models or the singularities.
Yes, of course. Yeah, but it is yes, we can explain in such a way, but I'm sorry, but I have to say didn't want to explain that part because it takes too much time. But anyway,
But
so
it's the same triangle.
the same triangulated category due to the book buys all of the seven. They are all triangulated. So there are three kinds of algebraic objects. So this category of matrix factorizations and the category of singularities and the category of maximal Cohen-Macaulay models, they are all equivalent. It is the statement by Bookwards and all. But I'm sorry, today I skipped that. Okay. Just And so if it, so so here is a particular matrix factorization. But if we forget about these maps, and if we how to say use these grading parts only, this one, but still it gives an important thing. It's essentially the same as the how to say this class in the Grothendieck group, but there is a little bit slight difference. So, but anyway, the important idea is to use these degrees, and there is a similarity to this class in the reduced homological, the Milnor fiber. So essentially, this one and this part. Is So later I'll explain, but we can usually forget about this degree of error, at least in the Grothendieck level. So this is the first appearance of the homology class in the matrix factor, graded matrix factor. And in order to make this correspondence or observation precise, we need topological mirror symmetry isomorphism and gamma interval structure for the matrix factor. So this will be the topic tomorrow. Anyway, so this is important. But essentially, for chain type inverted polynomial, this idea is essential, or the key to understand the category. And so this is just I prepare the definition. But anyway, as usual, we can consider the homomorphism and null homomorphism and so on. So we can consider the homotopy category. That's what I want to say. And so we can consider the category of graded model factorizations. And it is triangulated category with nice properties. The second one is a little bit non-trivial, but we can do it. So anyway, so this means the category is closed under taking direct sum. That's also important point. And if we consider this property in the ungraded case, we need to complete the polynomial formal power series. Or we need to, how to say, consider the idempotent completion of the matrix factorization. Anyway, so I think it's also well known. And so, yeah, I just pick all the definition of the or some order equivalences, the grading shift and translation. And what I want to say is this property, the last property, this one. Together with these definitions, it directly follows this property. This is also very important. So therefore, by this property, we can forget about the grading shift by f, because it is the same as the twice of the translation. So I just by this, sorry, I just wanted to say this property. Now, by the Alexander-Ryan theory, we can show that we can show the existence of self-functor, and it is given explicitly in this way. And by using this, and together with the previous property of this relation between translation and degree shift, we see that this category is fractional category. It's very easy to show.
So the construction of the category did not depend on the particular case that you're looking at for invertible polynomials, but this proposition.
This is a very general story.
Given proposition 26.
Yes, this is also general story.
For isolated hypersurface.
Yes, And in order to show the, I'm sorry, but I skipped that part. But in order to show this, we use the equivalence between the category of maximum common module or singularity categories. Or it's in order to state this, in order to this statement, we may use another equivalent category. It's convenient.
To define LF, you're assuming the F is weighted homogeneous
To
this grading LF.
We can also define LF for any weighted homogeneous polynomial, but usually or generically it is isomorphic to Z. So it's how to say LF is in some sense enhanced. So therefore it is a very special property of the invertible. It is among many weighted homogeneous polynomials, they are very special. The symmetry enhances. So therefore, if we deform the inverted polynomial, so first, or if even if it's weighted homogeneous, LF will be Z.
So, sorry, just to make sure, in proposition 26, you assume that F is weighted homogeneous.
No. Here we need to consider inverted polynomial. But taking a quotient, the same story holds for weighted homogeneous polynomial.
Okay.
Yeah, so how to say, we can downgrade the symmetry. So just a moment. Instead, we can use this as again, we get the similar story. In that case, we will have how to say, usually without this Caviar category.
And without assuming that F is weighted homogeneous, is there a relation between the self-functor and
Without showing. In that case, I'm sorry, I don't know well, but so this is very particular property of the no. Some ungraded version, and in order to have Caviar property, we don't need weighted homogeneity. Always, in some sense, Caviar because I'm sorry, but anyway, we know the result or the answer. So as I explained, so here we have this. So categorical. So this is the this is isomorphic to the homology group of the ungraded version of the matrix factorization, and this is the homology group of the ungraded version of the matrix factorization category for arbitrary polynomial defining isolated singularity. So therefore, we don't need weighted homogeneity to get the Caviar property. But anyway, so what I want to say is that if we consider the invertible polynomial and the certain graded version, it's very easy to have this property. And I'm sorry, and again, I'm sorry, I made a mistake. So this statement is the, what to say, in order to prove the existence of self-functor, we don't need to assume the weighted homogeneous property. And it is a general story by Auslander Leiden. So we can just assume that, so if we start from, if we consider the matrix factorization, we only need to start from the how to say, from polynomial or from a function with isolated critical points. That's enough.
Associates, and you do not have the gradient, right?
Yeah. So therefore, in that case, we have the self-functor which is Caviar in some sense, in the what is the graded sense. So in some sense, it's a bit complicated. And now, just I'm sorry, minus 5 minutes left. So this is just a statement of homological mirror-symmetric conjecture. And because the invertible polynomial and this area behaves very well, so I mean in this way, behave in this way. So in the DC categorical sense, this is true, but in the triangular category, we need to how to say make precise. But anyway, so therefore, so in considering homological mirror symmetry, we may assume that F is of chain type or root type. And there are many works by many people. So therefore, I don't mention the some particular known results and so on.
So that's for invertible polynomials.
Yes. For invertible polynomials, and especially so if F is of chain type, then by this work, the how to say the equivalence between this the first one and the last one is shown. As far as I understand. And now,
So when you strengthen the category viewpoint, you have exceptional collections.
Yeah.
So what would be the role? So under this conjecture, what would be the role of the exceptional collections in the matrix factorizations?
yeah. So I mean, so here, yeah, maybe tomorrow I'll explain, but it's very easy. So exceptional collection is very nice generator of category, and by using this description, it's very easy to find a good matrix factorization. So we don't have mathematically precise notion of the goodness. But anyway, so here looking at the object matrix factorization, we can say that this is good, this is not. So it's just the intuition. But anyway, by choosing enough number of good one, we can form a generator of expression. Then we can understand that to some extent the structure of this part. And if we believe in the equivalence, then we can find something here. We can connect object and object, and then later by using some story, a difficult story, one can have the categorical. But it's a very difficult one.
So does this imply the mirror symmetry for E polynomials that you had before?
Unfortunately not. Maybe in the last part I'll explain a bit. Sorry, maybe I'd like to continue. So because I don't have time. So anyway, so this is a possible application or the relationship with the classical singularities. So this is a problem, a modified version of your status problem. And so the initial data was F or F tilde. So in the singularity side, it was F tilde. And so by using geometry, we can have the generalized rules and so on. But the problem is, so because this is controlled by very combinatorial data and by an invertible matrix, and also the root system and so on are also combinatorial or algebraic objects. So he asked whether there is a nice way to avoid the geometry. But as I said, because I don't have any time, so I skipped. But anyway, so the possible idea is to use the homological mirror symmetry. And the point is here is that so starting from F or the matrix E, we have weights and also exponents. And also this is the problem in singularities. So there are many Coxeter-Dinkin diagrams, and among them, we want to have the good one or canonical one and a special one. So in general, we don't have that one because they are in some sense they are the same on the same level. But in the AD cases, they are very special thinking type, Hokusai thinking type. The usual one, thinking type. So it's natural to ask, in general case, whether it's possible to have some canonical one or special one. Again, I suspect this should be possible by using the homological symmetry or the I didn't write, but breaks down the notion of stability condition. But so, and the last part is somehow related to your question and combust to this. So starting from the root system or category, whether it's possible to recover the exponents of Hodge numbers. And at present, it's impossible. We don't know how to do that. And also, I don't have a good idea to recover the E function or Hodge numbers or the exponent. Yeah, at least, of course, the category is the fractional Calabi. We can recover the difference of the largest exponent and the minimal exponent, but almost it's at present it's we only know that we can recover the such dimension. We don't know how to recover the Hodge numbers. And it's related to the famous important and unsolved problem, recovery of Hodge numbers of, for example, Calabi manifold from its derived category. I think it's still an open problem. But anyway, so this kind of problems, some relationship between exponents and weights, there are, how to say, many important and